Welcome to the Deep Dive. Today, we are going deep,
Ooh, I like
literally into the Earth,
Okay.
to explore the crust and the mantle.
Right.
These layers, they might be hidden,
Right.
but they are the dynamic duo behind everything we see,
Total.
like on the surface.
Yeah.
You ready to uncover some underground secrets?
Anyway.
Okay. The source material we have today is full of slides.
Okay.
Like, we have a geology professor on speed dial explaining all this stuff.
Awesome.
I am so intrigued. So, to start,
Yeah.
I know the Earth has layers,
Right.
like an onion,
Okay.
crust, mantle, and then the core.
Mm-hmm.
Can you refresh my memory on all those specifics?
Absolutely. Yeah, you got the order right. Crust, mantle, which is the thickest part.
Right.
And then finally, the core.
Okay.
Right in the center.
Got it.
But it's more dynamic than an onion.
Okay.
Think molten metals swirling,
Whoa.
rock flowing, like super, super slow motion onion.
Okay, that's way cooler than an onion.
Yeah. Right.
Okay, so focusing on the crust and mantle,
Yeah.
what are the key differences?
Okay.
I know we're standing on the crust.
Right.
It's incredibly thin compared to the mantle.
Exactly. The crust is like this delicate skin of the earth.
Right.
The mantle, the bulk. Think of it this way.
Mm-hmm.
If the earth were a peach,
Okay.
the crust would be the skin,
Right.
the mantle, the juicy fruit,
Okay.
and the core, the pit.
That makes sense.
Huh.
But skin seems too fragile.
Uh-huh.
The crust is solid rock.
Solid rock, yes.
All right.
But it's still incredibly thin compared to the mantle.
Okay.
And it comes in two main types.
Okay.
So we've got continental crust,
Okay.
which makes up the continents.
Mm-hmm.
It's thicker and mostly granite.
Gotcha.
Then there's oceanic crusts
Right.
under the oceans.
Yeah.
Thinner,
Oh.
denser, mostly basalt.
So that's why the continents are above sea level,
Ah.
literally sitting on thicker crust.
Exactly.
It's like they're floating higher.
That's a great observation.
Thanks.
And it leads us to the concept of isostasy.
Okay.
Basically, it means the Earth's lithosphere.
Okay.
That's the crust plus the very top bit of the mantle.
Hold on. New term alert.
Haha.
Lithosphere.
Mm-hmm.
So it's crust and a bit of the mantle.
Yeah.
Oh, so those tectonic plates,
Yes.
they're actually chunks of the lithosphere moving around.
Exactly.
Not just the crust itself.
Yeah, it's like the crust and the uppermost mantle are like glued together,
Okay.
forming this rigid outer shell.
Hmm.
And this lithosphere is what breaks into the tectonic plates.
Okay.
And you're right. These
Uh-huh.
plates are constantly on the move,
Yeah.
like pieces of a giant, incredibly slow-motion jigsaw puzzle.
Wow.
Yeah.
So back to isostasy.
Okay.
How does this floating balance work?
So imagine a seesaw.
Okay, a seesaw.
Yeah.
But
with
what?
the thicker continental crust as a heavier person
Oh.
on one side, and the thinner oceanic crust as a lighter person on the other.
Okay, I see.
The heavier side, the continents, sit higher,
Yeah.
while the lighter side, the ocean basins, sit lower.
Yeah.
It's all about achieving that equilibrium
Got it.
on the denser mantle below.
Okay, so it's all about density and buoyancy.
Yeah,
That means things on the surface
right.
can affect what's happening deeper down.
Yeah,
Like mountains.
exactly.
They're massive.
They are.
Do they push down into the mantle more?
That's where it gets really interesting.
Okay.
Mountains actually have roots
What?
that extend deep.
Wait, mountains have roots.
They do.
Whoa.
Yeah, these roots are like a counterbalance,
All right.
providing buoyancy and
Oh.
support to those massive peaks above.
So it's not just about what we see cowering above us.
Right.
There's a whole hidden world beneath the surface.
Exactly.
Wow.
These mountain roots are essential for stability.
Okay.
Think of it like a ship.
Okay.
It needs a deep keel
Right.
to counterbalance the weight of the sails
Yeah.
and stay upright. Mountains need those deep roots to support their massive weight
Okay.
and maintain balance.
Wow, this is blowing my mind.
I know.
Okay. So the lithosphere, with its mountains and continents and everything, it's floating on the mantle.
Yeah.
But what's actually happening in the mantle that makes the plates move?
Now we're getting to the engine of plate tectonics.
Oh, exciting.
It's all about heat and movement.
Okay.
Remember those convection currents we talked about?
Right, like when water boils,
Yes.
hot stuff rises, cools,
Yes.
sinks, repeat.
Exactly. The same thing happens in the mantle. But instead of water,
Yeah,
it's hot, semi-solid rock.
okay,
Heat from the Earth's core
right.
causes these massive convection currents in the mantle.
Wow.
It's a slow motion churn.
Yeah.
But incredibly powerful.
Okay.
And it's what drives the movement of the tectonic plates above.
So picture this.
Okay.
We've got the lithosphere with its crust and a bit of mantle.
Yeah.
All broken into these tectonic plates.
Right.
And these plates are slowly gliding around on top of the mantle.
Exactly.
Which itself is churning away with these convection currents.
It's like a giant
Oh my gosh.
slow motion dance.
It's a very, very slow dance.
A very, very slow dance.
What do we guess?
Yeah. And it's not just any part of the mantle that the plates are moving on.
Oh.
There's a specific layer called the Asthenosphere.
Asthenosphere.
Yes.
Another new term.
I know, there's a lot of them.
What's so special about this layer?
So the Asthenosphere is right beneath the lithosphere.
Okay.
It's still part of the upper mantle,
Mm-hmm.
but it's hotter and weaker.
Okay.
More like, imagine super thick,
Okay.
warm, silly pudding.
Silly putty.
Yeah.
So the rigid tectonic plates are actually surfing on this warm,
Yeah.
gooey layer.
Pretty much.
That seems so counterintuitive.
It does.
Wow.
But that's how it works. The asthenosphere's unique consistency allows the tectonic plates to move, albeit very slowly.
Okay.
It's crucial for the whole process of plate tectonics.
So we've got this constant interplay.
Right.
The rigid lithosphere on top
Yeah.
with the crust and the continents we know, and this slowly flowing asthenosphere beneath,
Yes.
driven by heat from the core.
It's a fascinating dance of forces
Right.
shaping everything we see on the surface.
It's amazing.
I know.
I'm definitely hooked.
Good.
We're going to need a whole lot more deep diving to unpack all of this.
I agree.
This is just the tip of the iceberg.
For sure. It really is a dynamic system. And speaking of interactions,
Okay.
remember those tectonic plates we've been talking about?
Yes.
Their constant movements aren't just some abstract thing.
Right.
They're literally shaping the Earth's surface.
Okay, so remind me.
Yeah.
The lithosphere broken into plates, moving thanks to the asthenosphere.
Exactly.
What happens when these plates bump into each other? I know it's not a gentle process.
Definitely not.
Yeah.
We're talking massive forces at play.
Okay.
Basically, there are three main ways that these plates interact.
Okay.
Divergent, convergent, and transform boundaries.
Divergent, convergent, transform.
Yeah.
I remember those terms from school,
Right.
but I need a refresher.
Okay. Sure.
Let's start with divergent.
Okay.
What's happening at those boundaries?
Divergent is where plates are moving apart,
Right.
pulling away from each other.
They're like separating.
Yeah, imagine a crack opening up in the Earth.
Okay.
That gap doesn't stay empty for long.
Right.
Magma, molten rock from the mantle, rises up to fill it,
Okay.
creating new crust as it cools and solidifies.
So it's like the Earth is constantly birthing new crust
Pretty much.
at these divergent boundaries.
Uh-huh.
Where can we see this in action?
The Mid-Atlantic Ridge
Okay.
is a classic example.
Okay.
It's a massive underwater mountain range that runs down the middle of the Atlantic Ocean.
Oh.
It's basically a giant rift zone
Hmm.
where new crust is being formed as the North American and Eurasian plates pull apart.
Wait, so the Atlantic Ocean is actually getting wider?
It is.
That blows my mind.
I know, right?
Just a tiny bit every year.
A tiny bit wider each year.
Wow. All thanks to those divergent boundaries.
Yeah. Pretty cool.
Convergent boundaries.
Yeah.
Those are where things get more intense.
They do.
How? Intense how?
Well,
Isn't it just plates pushing together?
it is. But imagine the force involved.
Yeah.
When two massive plates collide,
I can't even imagine.
what happens depends on the type of crust involved.
Okay.
Oceanic crust is denser than continental crust.
Right.
So when they meet,
The denser one sinks.
exactly.
Like a geological game of King of the Hill.
Haha. Yeah, you could say
Like,
the denser oceanic plate gets forced down or subducted beneath the lighter continental plate.
right.
It's a process called
That's suction.
subduction.
Okay, so subduction, one plate goes under.
Yes.
What happens then?
Well,
Does it just melt away down there?
it does eventually get recycled back into the mantle, but not without a dramatic exit.
Ooh, okay.
Subduction zones are responsible for some of the most impressive features on Earth.
Give me some examples.
Think deep ocean trenches,
Okay.
like the Mariana Trench, the deepest point on Earth. And then as the subducting plate sinks,
Okay.
it releases fluids that cause the mantle above to melt.
Oh.
That molten rock or magma
Yeah.
rises up and boom, volcanoes.
So those chains of volcanoes we see along coastlines,
Yes.
like the Andes Mountains in South America,
Exactly.
those are formed because of subduction.
It's a perfect example.
It's like the Earth's way of recycling, but with fiery consequences.
Exactly.
So the Andes are the result of...
The Nazca Plate,
Yeah?
which is an oceanic plate,
Right.
subducting beneath the South American plate, a continental plate.
Okay, got it.
And that brings us to the other scenario.
Right.
What happens when two continental plates collide?
No more subduction then.
Nope.
They're both too buoyant to sink.
Exactly. It's like pushing two equally strong opponents together.
Right.
They can't go under each other, so they buckle and fold,
Yeah.
pushing upwards.
Okay.
And that's how we get massive mountain ranges.
Makes sense.
Like the Himalayas.
So the Himalayas, the tallest mountains in the world,
Yeah.
are basically a giant continental crumple zone.
You got it.
Wow.
The Indian plate collided with the Eurasian plate millions of years ago.
Okay.
And they're still pushing into each other today.
Oh, wow.
That's why the Himalayas are still growing,
They're still growing.
albeit very slowly.
Wow. It's hard to wrap my head around these timescales, millions of years.
I know, it's a long time.
Okay, so we've covered divergent
Right.
and convergent boundaries.
Yeah.
What about transform boundaries?
Transform boundaries are where plates slide horizontally past each other.
Oh.
Think of it like trying to move two bricks past each other on a table.
Okay, I'm picturing it.
They're going to scrape and grind.
So lots of friction,
Yes.
but no dramatic sinking or mountain building.
Right.
Okay.
But that friction can be incredibly powerful.
Right.
Building up stress
Okay.
until it releases
Right.
in the form of earthquakes.
Oh, okay.
The San Andreas Fault in California is a prime example.
Right. Yeah.
The Pacific Plate is sliding past the North American Plate,
Okay.
and that's why California is prone to earthquakes.
So transform boundaries are basically giant geological fault lines.
Exactly. And those faults are constantly moving, even if we don't feel it most of the time.
Right.
It's a constant reminder that the Earth is dynamic,
Yeah.
always changing beneath our feet.
I'm still stuck on this idea of continents moving over millions of years.
Yeah.
I remember learning about Pangaea,
Right?
the supercontinent,
Uh-huh.
breaking apart.
Yeah.
Is there any way to know how the continents were arranged before that?
That's a great question. It's like trying to solve a giant jigsaw puzzle.
Yeah.
Where the pieces have been moving for millions of years,
Right.
but geologists have a few tricks up their sleeves.
Like what?
They study things like the distribution of fossils,
Okay.
types of rocks found in different locations,
Hmm.
and even the magnetic signatures preserved in ancient rocks.
Magnetic signatures.
Yeah,
Rocks can be magnetic.
they can.
I have no idea.
It's called paleomagnetism.
Paleomagnetism.
Yeah, okay.
When rocks form,
Right.
they record the direction of the Earth's magnetic field at that time by studying those magnetic signatures in rocks of different ages.
Okay.
Geologists can track the movements of continents relative to the Earth's magnetic poles over millions of years.
So it's like rocks have built-in compasses
Pretty much.
that tell us where they were located in the past.
Exactly.
That's incredible.
It is.
Yeah.
And by combining paleomagnetic data
Okay.
with other geological evidence.
Scientists have been able to reconstruct the positions of continents
Wow.
at different points in Earth's history,
Really?
going back hundreds of millions of years.
So we can actually see how the Earth's continents have danced around the globe
Okay.
throughout time.
Yeah.
What have they learned from these reconstructions?
They've learned that Pangaea
Right.
wasn't the first supercontinent.
What?
It turns out there have been several supercontinents
What?
throughout Earth's history,
Hmm.
forming and breaking apart in a cycle driven by those powerful forces in the mantle.
So it's like a cosmic ballet.
Exactly.
The continents swirling around the globe.
Yeah, it's pretty amazing.
Okay, that's a seriously epic dance.
Aha, it is.
So if the continents are still drifting,
Uh-huh.
what might the Earth look like millions of years from now?
Oh.
Are we headed for another Pangaea?
That's the million-dollar question.
Right.
It's hard to predict the future
Yeah.
with absolute certainty,
says-
but geologists have created computer models
Okay.
to simulate the movements of continents.
So we're using the past to
Yeah,
predict the future of continents.
exactly.
Right.
And some of these models suggest that in about 250 million years, the continents could converge again,
Really?
forming a new supercontinent. Some call it Pangaea Proxima.
Okay, but Pangaea Ultima.
Pangaea Proxima, it's got a nice ring to it.
Yeah.
So the continents might eventually reunite in a giant landmass,
They might.
But who knows what that supercontinent will look like
Right.
or where it will be located.
It's a reminder that the Earth is always changing,
Yeah.
always evolving.
And I, for one, am feeling the urge to keep digging.
Me too.
It is amazing to think about, these huge forces shaping the planet right beneath our feet.
It really is.
It's like we're living on a slow-motion roller coaster. But what I find fascinating
Yeah.
is how the mantle isn't just moving things around.
Right.
It's also creating new stuff.
It is. We talked about volcanoes forming at subduction zones.
Mm-hmm.
How does that tie into the different types of rocks we see all around us?
That's a great point. The mantle plays a crucial role in the rock cycle. It's like the ultimate recycler, transforming rocks from one type to another.
Okay, so remind me, what are the main types of rocks? I know there's igneous, sedimentary, and metamorphic.
Yeah.
How are they all connected?
You got it. It all starts with magma.
Okay.
That molten rock from the mantle.
Right.
When magma cools and solidifies, whether underground or after a volcanic eruption, it forms igneous rocks.
Okay.
Think granite, basalt, obsidian. They all come from cooled magma.
Oh, igneous rocks are like the original rocks.
Yeah,
straight from the mantle's kitchen.
Haha.
Yeah. Okay.
Now, over time, these igneous rocks get exposed to the elements.
Yeah.
Wind, rain, ice, all that weathering and erosion action, they get broken down into smaller pieces.
Okay.
Sediment, which gets carried away by rivers and eventually deposited in layers.
Okay.
Those layers get compacted and cemented together over time, forming sedimentary rocks like sandstone, limestone, and shale.
So sedimentary rocks are basically rock recycling.
Precisely.
Old rocks turned into new ones.
It's a beautiful cycle.
Right.
But the journey doesn't end there.
Oh, there's more?
There's more.
Okay.
If sedimentary rocks get buried deep enough, they get exposed to intense heat and pressure from the Earth's interior.
Okay.
That's where the magic of metamorphism happens.
Ooh, okay.
They get transformed without melting completely into metamorphic rocks like marble, slate, and gneiss.
So metamorphic rocks are like the ultimate survivors.
They are.
They've been through the ringer.
Right.
And come out transformed. It's incredible to think about the journey these rocks take over millions of years.
Oh, I know.
All thanks to the power of the mantle.
Yeah.
And it's not just rocks.
Right.
The mantle is also responsible for generating the Earth's magnetic field.
It is.
Which protects us from harmful solar radiation.
Absolutely.
Hold on. The magnetic field comes from the mantle.
Well,
I thought it was the core.
the core does play a part.
Okay.
It's the constant motion of molten iron in the outer core,
Right.
driven by heat from the even hotter inner core
Okay.
that generates electric currents.
Okay.
These currents, in turn, create a magnetic field
Okay.
that extends far out into space,
Right.
forming a protective bubble around our planet.
So the mantle is like the ultimate multitasker.
It really is.
Moving continents, creating mountains, recycling rocks,
Yeah.
and even powering our planet's magnetic shield. It's the unsung hero of Earth's story.
It's truly remarkable, and this incredible dynamism has profound implications for life on Earth.
Yeah. How so?
Well, think about the impact of continental drift on the evolution of life.
Okay.
When continents break apart, populations get separated,
Right.
leading to the development of new species as they adapt to different environments.
So the continents drifting apart is like nature's way of experimenting with evolution,
You could say that?
creating biodiversity hotspots all over the globe.
Yeah, and the formation of mountains,
Right.
driven by plate tectonics,
Yeah.
has created unique habitats with diverse ecosystems.
Okay.
From lush rainforests to high-altitude deserts.
This is all so interconnected.
I know, it's amazing.
It's like a giant web of processes all linked together.
Uh-huh.
It's a bit overwhelming,
Yeah.
but in a good way.
Uh-huh. I agree.
And it highlights the importance of understanding geological processes.
It does.
Not just for scientific curiosity,
Right.
but for practical reasons, too.
Absolutely.
We need to be aware of the potential hazards associated with earthquakes, volcanic eruptions, and other geological events.
We can't ignore the power of these forces.
Right, especially as populations grow and cities expand into areas
Right.
that might be vulnerable to these hazards.
Exactly. By studying the Earth's crust and mantle,
Okay.
we can learn to better predict and mitigate the risks associated with these natural hazards.
Oh.
It's about understanding the forces at work and how they might impact us.
So knowledge is power when it comes to living on a dynamic planet.
Absolutely. The more we understand about how our planet works,
Yeah.
the better equipped we are to live safely and sustainably.
This deep dive has definitely opened my eyes to the power and importance of the mantle.
Good.
It's not just some inert layer down there.
Right.
It's the driving force behind so much of what makes Earth unique.
It's been a pleasure exploring these fascinating topics with you.
Likewise.
Hopefully it sparks further curiosity in our listeners to continue digging deeper into the wonders of geology.
I think it's fitting to end our deep dive with a thought-provoking question.
Okay.
For everyone listening, we've talked about this incredible journey of Earth's continents over millions of years.
Right.
If this cycle of drifting and colliding continues, what might the Earth's map look like millions of years from now?
That is a great question.
Will familiar coastlines vanish? Will new mountain ranges rise from the depths of the ocean?
It's a question worth pondering.
Yeah.
The Earth is constantly evolving.
Right.
The only constant is change.
Well said.
So stay curious and keep exploring.
Thanks for joining us on this deep dive into the Earth's crust and mantle.
My pleasure.
Until next time, keep those minds digging.